This is section 10.1. We'll see this section is the first of three that are very closely related. We want to talk in detail about very specific graphs in x and y, the xy plane, called the conic sections. And you might have seen these before. The conic sections are just circles, ellipses, which we briefly got introduced to in the last lecture, hyperbolas, which we also briefly got introduced to, and parabolas. And we call these shapes conic sections because they are actually very closely related to this cone. You might think, why are there two parts to this cone in each of these pictures, an upper and a lower part? It turns out, and you'll see why in Calculus 3, when you write a general equation of a cone, it actually describes both halves of these, both the upper and lower parts of these cones all together in one equation. So it's typical to think of in mathematical terms, a cone is really both sides, what might look like a double cone. But it turns out these conic sections, a circle, an ellipse, a hyperbola, a parabola, these are just the cross sections of the cone with various different planes. So for example, in this first picture of a circle, if you have this cone that has this vertical axis of symmetry here, then any plane perpendicular to that direction, horizontal in this picture, is going to slice the cone in an intersection that makes a circle. Likewise, an ellipse is pretty similar, but it's where that plane is just tilted up a little bit, tilted in some direction. Right? In that case, we're saying it's not vertical, and it's not parallel with the slope of this surface here. It's not parallel to the slope of the surface of the ellipse, but it's some angle in between there. Sorry, not parallel to the surface, to the slope of the surface of the cone, I should say. But it slices that cone at some angle, and it makes this ellipse shape. It turns out when you turn this plane vertical, like in the next picture, that's when you're going to pick up some of this cone down below and some up above. Together, those two branches, the yellow curves there, those make what we call a hyperbola. Parabolas we're more familiar with. They are the very special case of slicing a cone with a plane that's actually parallel to the slope of this surface, right, of the surface of the cone. If you do that, you get one of these parabola shapes. Okay. So let's see. Yeah, let's go a little bit further here. Let's go ahead and define an ellipse, the first one we're going to talk about. We want to talk about these other shapes as well. Hopefully you know a little bit about circles. We'll see ellipse. Circles are just a specific case of an ellipse. But let's talk about this first shape, the ellipse here. We'll start out talking about the graph of this ellipse centered at the origin in the xy plane. So the sorts of pictures you can think of are these two pictures over here on this side. Right, a graph, let me zoom out just a little bit. Yeah, a graph like this or this. Right, that's an ellipse. So the definition though, these pictures are nice up here with this cone, but it gives us no sense of what we think of an ellipse being mathematically, why it's a useful sort of shape. The definition of an ellipse is that an ellipse is the set of all points x, y in the plane such that the sum of the distances between x, y, and two fixed points is a constant. Those fixed points are called the foci, plural of focus, of the ellipse. So what we're saying is that in, for example, this picture down here, let me see if I can draw on this. In this picture down here, if I choose any point on this curve, maybe this point here, the distance from one of these foci plus the distance to the other, that is the same as, let's see if I can do a different color. Maybe I'll use green. That is the same as the distance from any other point on here. So maybe we choose this point. The sum of the distances from that point to the foci. The green length from this focus to the ellipse out to the other focus is equal to the black length out from one focus to the ellipse to the other focus. No matter where we put those 2 points, the black point on the ellipse or the green point on the ellipse, the sum of those distances is equal. Right? It's constant. That's a nice way to think about this. Right? It's a constant. Now the line through those foci, intersects the ellipse in 2 points called the vertices. We've got those labeled here. That's just plural vertex. Here's a vertex and here's a vertex. Notice these points at the top and bottom, those are not vertices because the line connecting those doesn't go through the foci. These foci are these points out here and out here. That line connecting those vertices, we call that the major axis of the ellipse. So it's the longer distance across the ellipse. The other line connecting the top and bottom points of this ellipse, the shorter distance across, is called the minor axis. And the center is exactly what you think. It's the center. It's halfway between, it's the midpoint of the major axis. Midpoint of the segment connecting the vertices. So let's look a little bit further here. We have a bunch of facts here we want to use. Right? We're going to start out and assume A and B are positive numbers. Then if we assume that, then we can say that these are the equations of an ellipse with a major axis on the x-axis or on the y, centered at the origin. So these are really the equations of these pictures we're picturing here, but in both of these equations, we're saying the length of the major axis is 2a. So whatever squared value we have here, that value without the square, that's like the distance from the center out to the vertex. From vertex to vertex is 2 times that, is 2a. But let's clean this up a little. Yeah, the distance from here to here, that's a distance of 2a. 2a. The length of the minor axis from here to here, that's 2b. And if we call those distances 2a and 2b, then this becomes the equation of our ellipse. Now you might say, well, where are those foci located? Those foci are located at points C0, negative C0. So saying that the distance from the foci to the center is C units. The distance between the foci together is 2c. But those are where those distances we call c. And the connection between all these lengths, the distance from the center out to the vertices or in the other direction, those are our a and b values, and the distance from the center to the foci, the c value, they're related by this equation, which is kind of tucked away over here, but it's actually very important. Right. In this sort of arrangement, we always call the location of the vertices, those are a distance a away from the origin. So for this horizontally oriented major axis, right, a major axis along the x-axis, that'll mean our vertices are at negative a0 and a0. Likewise, the minor axis, the vertical one, will go from zero negative b up to 0 positive b. So that's where we get these endpoints of the major axis, of the minor axis. Right, so here in this picture is really, in these pictures down here, are really all these equations put together like I've been describing. Notice we haven't labeled it, but we have the major axis is the longer axis, the minor axis is the shorter axis, the location of these foci is C, the distance from the center to these foci is C, the distance from the center to the vertices is A, and B up to the endpoints of the minor vertex. And that's exactly the same if we think of everything having a major axis, a longer axis along the vertical direction. All we're going to do, though, is interchange the a and b values. We're going to call the bigger of those ones, we're going to put the bigger of those numbers, a and b, we're going to put that one under the variable whose axis we have, right? So the y variable has the major axis. So we put the bigger number, the a value, under y. And these formulas flip around a little bit, right? The c value, the distance of the foci, is now in the y direction from the center. So we put those in the y coordinates to get the coordinates of the foci. But it's all the same geometry here, right? These pictures make it pretty clear to remember these formulas. You might say, well, how do we know this works? I'm not going to give it's actually a lot of complicated algebra. If you were interested in some extra credit, maybe that'd be a good sort of argument to try to hash out. How do these equations match up with this definition? But I don't want to prove that. Maybe we do just show a little thing about a little sanity check here. The way I think about an ellipse is that it's like a circle. Or let's view it this way. If I have a and b are equal, so I go the same distance vertically as I do horizontally on my ellipse. A and b are the distances you go out to the edges of your ellipse in both the x and y direction. If both of those are the same number, what do I have? Visually, it looks like I have a circle. According to this equation, I would have, multiply both sides by a squared, I would have a circle of radius a centered at the origin. So there's a lot of sense to make of this ellipse by thinking of it as a circle where the radius in the x direction, regardless of the picture, the radius in the x direction differs from the radius in the y direction, the vertical direction, right? It's like a circle that doesn't know what its radius really wants to be. In two different directions, there's two different radii. In the x, you go a certain amount, but in the y, you go a different amount. So that's a nice intuitive way to think about what an ellipse really is. It's like a circle where there's kind of a tug of war between the radii, the radius in the x direction and the radius in the y direction. And in this sort of way of thinking, the a value, or you can think of the numbers divided under each of the variables, as just telling you the radius squared in that direction, right? For example, if we have this first picture, horizontal major axis, then this first equation is telling us that whatever x squared is divided by, that's the radius squared in the x direction. So in this case, a is how far you go in the x direction. B is how far you go in the y direction from the origin, from the center, I should say. Right? So you can kind of think of it that way. It's like a circle that can't make up its mind. It doesn't know what it wants its radius to be. So it just splits the difference. Certain radius in the x direction, different radius in the y direction. So let's jump into this example here. I think this will be pretty quick and easy. Let's graph the ellipse, identify the center, foci, and vertices. First here, we want to identify the bigger number represented. That's our a squared. The lesser numbers are b squared. We'll use that to figure out our foci. I think just looking at the equation and thinking of those sort of two different radii in different directions is the easiest way to sketch this. It's saying the distance in the x direction that we need to go, the distance in the x direction, is the square root of 25. So that's 5 units in the x direction to get to the edge of our ellipse from the center. In the y direction, go 2 units, the square root of 4. There we go. We've pretty much got it. We do want to identify the center. That's 0, 0, right? Because this is of the form. This has the right form to match these equations, which were all centered at the origin. So the center is still at the origin, which I've marked over here. Foci we need to think about a little bit. Remember, c squared equals a squared minus b squared, right? The distance from the center to our foci is a squared, well, that distance squared, c squared, is a squared minus b squared. So it's just, in this case, 25 minus 4, which is 21. So c is root 21. Root 21's between 4 and 5, so it's about here, maybe. And here. Remember, that's along, I put those c values, this distance c out to the foci, because I put it on the x-axis because it's on the major axis. The foci sit on the major axis, the longer of the two. And then we just do our best to sketch an ellipse in here. Oh, I guess I should say, let's write out the answers. Center, 0, 0. Foci, we can say, are at 0, plus or minus root 21, comma 0. Here's one of them, here's the other. And the vertices are the ends of that major axis, the endpoints, which are at negative 5, 0, and 5, 0, which you could just write as plus or minus 5, 0. It's the same thing. I think in Connect it'll probably ask you for both points written out separately, not the plus or minus. So better to write them both. Okay, so that's all our information we were asked for. Let's just sketch this graph. Just doing your best. Sketch a smooth curve. That's about the best I'm going to be able to do, so I won't try again on that. Maybe I label these out here. This focus was negative root 21, 0. This focus is positive root 21, 0. Squeeze it in there, fit it. Okay. That's about all we're looking for. You got all the big features there. We know it's an ellipse, and we answered specifically about those quantities we were asked about, the center, foci, and vertices. Let's do another one here. Maybe this would be a good time to try this if you want to pause the video, if you have a sense of how to do this. Otherwise, I'm going to jump in here. So to do this, I need to first put it in that correct form, which notice always had a 1 on the right-hand side. Remember, this form of our equation and this form of our equation always had a 1 over on the right-hand side. So to really make these a and b values be meaningful, we better match that form. We better divide both sides by 441. Leaving a 1 over here. And so let's see what happens when I divide those numbers. I get 49, well, let's see how many times. 441 divided by 49, I get that is 9. So I could rewrite this as x squared over 9. That means 9 over 441 would leave a 49 in the bottom. You can do that math. And that's what we have. So now this is pretty easy to kind of decipher and plot, right? We can think about which case of equations we're in really hard over here, or we can just think about going 3 units away from the origin in the x direction and 7 units away from the origin in the y direction. Once it's in this form, we don't have to think very hard at all. 3 units in either direction from the origin in the x direction, and 7 units away from the origin in the y direction in both directions. So we have that our a value is this guy, the bigger guy. A squared's 49, b squared's the smaller one, 9. So we can find c squared very easily. C squared is a squared minus b squared. Looks like c is root 40, which is 2 root 10. Right, so 2 root 10, let's see roughly how big that is. I mean, root 40, we can tell that's going to be between 6 and 7. So it's somewhere up here and somewhere down here. The c values are very close to the a values in this case. 40 is very close to 49. And so we have all our information. Let's identify the center is still the origin. The foci, well, now these are on a vertical axis, right? So these are going to be 0, comma, negative 2 root 10. Clean that up a little. 2 root 10. And 0 comma positive 2 root 10. The vertices again are on the vertical axis now. So those will be 0 comma, how high did we go? 7 units. And 0 comma, I'll put my negative first, doesn't matter. 0 comma 7. Right. So we have all our information. We just draw pictures carefully as we can. It's not going to be perfect. That's okay. There we go. Rough it in there. It's all right if it's not perfect. Okay. There we go. Good enough. Maybe I label my vertex at 7, 0, 7. Really, if you label one of these and the other, you don't have to do the negatives. If we know it's an ellipse, we know the symmetry is there. And these foci, the top focus is at 0, 2 root 10. And the bottom focus down here, 0, negative 2 root 10. Right? So I think we've got it all. That's our picture, and those are our details all laid out for us. So now we want to think about how, remember, if we were graphing an equation like y equals f of x, we've seen that transformations of this would tell us that if I did these transformations, I would shift h in the x direction, right? Subtracting h from x means you're moving the whole graph that you started with h units in the x direction. And notice this is also whatever you add outside the function, that's you move that many units in the y direction. But notice that's just saying that y minus k equals f of x minus h really is implying those same transformations to graph something of this form, which is really just what we started with, y equals f of x, just with a h subtracted from the x and a k subtracted from the y. This is true in general for equations. That whatever you're subtracting from your y value in your equation, you're shifting that many units in the y direction. And whatever you subtract from your x value in your equation, you're shifting that many units in the x direction. Right? And when I say that many units, if you are subtracting a negative, for example, you would go negative in the x direction. But subtracting a negative is really like adding a number here. So that's how we get that plus inside, meaning a shift left in the x direction, the negative x direction. So with that in mind, we can actually think of these ellipses shifted with their center at some other point hk. All we're going to do is take the previous equations and subtract h from the x in both and k from the y in both. Now that's going to shift where our foci sit, but it's just a simple shift, right? We know how to add h to all the x coordinates and y to all the y coordinates to get our new locations of these values. And same with the endpoints of the vertices and all that, right? So our new picture kind of looks like this. All the a, b, and c values, they're still all accurate relative to distances from the center, right? Distances measured from the center. It's just our centers moved around, and that really doesn't make it that much more difficult to express in an equation or to find the center, foci, vertices, all that for. So for example here, graph this ellipse, identify the center, focus, foci, and endpoints of the minor axis. Hope I did that right in the previous ones. Yeah, as for vertices, okay. So let's do this. Graph the ellipse, identify the center, foci, and endpoints of the minor axis. Right away, we just want to identify where have we shifted to. We've subtracted -2 from x. So that's how far we shift in the x direction. And we have subtracted 3 from y. So that's how far we move in the y direction. So instead of being centered at the origin, we're just centered at -2, +3, right here. Everything else works the same. You just now graph the same picture around that center point. For instance, having a 16 under the x stuff tells us we go 4 units in either direction from the center along the x. 4 units in either direction. So that puts me at 2, 4 over here, just from looking at my graph, and -6, 4 over here. Oh, 3, sorry, not 4. The height was 3, right? The center's at -2, 3. And so I know my a value is the bigger of these, well, a squared at least. My b value is the smaller. Right away I can find my c value to be 7, so c is √7, almost 3, a little less than 3. So this is saying if I want to find the center, I've already got that. That's my center. If I want to find the foci, I'm still just going from this center point in the direction of the major axis, so that's the x direction, since x has the bigger number. We're going a distance √7 from this point where we're starting. So that's just less than 3 units in either direction from here. Maybe about here, and maybe about, that'd be 3, so a little less. There's one focus, there's the other focus. Okay. So I'm going to write down coordinates of these guys. F1, the focus I've labeled over here to the left, that starts at an x coordinate of -2, and then we take away √7 from that. Starts at -2, and we take away -7 from that. Right? And the y coordinate there is still 0. The other focus, we start at the center, -2, and we add √7. And our y coordinate's still 3. Okay. So we have our foci. I won't even try to label these on my picture. I put the F1 and F2 and give their coordinates over here. That's good. I don't want to clutter up my picture too much. I guess we should label the endpoints of the minor axis. We've already found the vertices, the endpoints of the major axis. Those are 2, 3, and -6, 3. Let's figure it out for the minor axis, though. For the minor axis, we have 3 units away from the center. So that's here and here. Looks like -2, 6. And this guy looks like -2, 0. So the minor axis has endpoints -2, 6, -2, 0. Okay. From that, we can kind of see our picture. We just sketch it as smoothly as we can, not worrying too much if it's not great. Because I don't want that. Okay, pretty disappointing. I know I said don't worry about it, but I want it a little better. Good enough. We'll stop there even though I made it into an egg. Okay. And that's all the detail you need. So long as you label things, no one can really fault you so much for having less than perfect pictures. Okay, so this is the next step. We want to take an equation that's not yet in a recognizable form of an ellipse and see how to convert it to that form. And the process to do this is just completing the square. Okay. Okay, so let's try this. I think I fixed that font there. So I'm going to take this and I want to group all the x terms together and group all the y terms together. By grouping, I just mean write them sequentially near each other. You're not really changing anything. And any constant I have, I want to just move that to the other side. So from here, what I want to do is look at each of these guys, and to complete the square, I really want to get rid of the coefficient on the squared term. So for example, in the x terms, I want to factor out that 9 and see what that leaves behind. And I'll leave some room inside the parentheses to complete the square, right there. Also, in this next piece, the y stuff, I'll factor out that 5 to get rid of that coefficient. And that leaves y squared minus 6y. Again, leave some space to complete the square and continue. And remember, to complete the square, we need to add 1/2 the linear coefficient, so that's the 2 in this case, squared. If we do that, it's going to make this whole trinomial here factor down very nicely. But keep in mind what we've done. We've added 1/2 of 2 quantity squared inside the parentheses, but if you distributed this 9, that's actually 9 times this quantity that we actually added to the left-hand side of the equation. So we better add 9 times that quantity to this side as well to balance the equation. And we'll do the same thing here. We're going to add 1/2 of that linear coefficient squared. We're going to add that here. Same idea though, we got to balance the equation. We added this inside the parentheses, but it's being multiplied by that 5. So we really added 5 times that to the left side. Let's add 5 times that to the right side to balance. And now we want to clean this up. We're going to get here 9 times this trinomial. If we've completed the square correctly, will just be x followed by whatever 1/2 the linear coefficient is. So 1 in this case, positive 1, quantity squared. That's how that will factor down. That's why we call this completing the square, because this factors as a perfect square. Plus 5 times, well, what do you get in the y value? We should have, following the same rule, y, and we just get whatever half that linear coefficient was, so -3 minus 3, quantity squared, equals, and on the other side, we've got to do some work here. We have -9 plus, looks like this stuff is 9 times 1, so those cancel, plus 5 times 1/2 of -6, which is -3, squared. -3 squared is 9. It looks like we have 9 times x plus 1 squared plus 5 times y minus 3 squared equals 45. And now we're almost home free. Now it's pretty easy to put this in a standard form. X plus 1 squared, divide both sides by 45 to do that. Right, that standard form has a 1 on this side of the equation, so we better divide that 45 off to put a square there, or to put a 1 there. So we get 9x plus 1 squared over 45 plus 5y minus 3 squared over 45 equals 1. And we make cancellations. Home free. Looks like our final equation is this, which is going to be very simple to sketch now that we have the picture, right? We know that the bigger number is our a squared. Tells us this is going to have a vertical major axis since the bigger number is under the y. 5 is our b squared. Kind of a weird number. Doesn't have to be a perfect square there. That's fine. B is just root 5, right? No big worries. That means c squared is 9 minus 5 equals 4. So c is 2. That's kind of nice. But now from here, we've kind of figured out all the important parts. Let's go ahead and sketch this thing. We need to go root 5 units in the x direction from the center. Maybe we start there. The center is -1 and 3. -1, 3. That's where we're starting. And so let's see here. I need to go root 5 from that center point, root 5 in either direction from there. So this center point, let's label it -1, 3. If I go root 5 in the x direction to the right, looks like you get 1.23 roughly. Oops, not 0, but 1.23 roughly. All right, so this point will be -1 plus root 5, comma 3. That's not a focus, that's an endpoint of the minor axis. And we go the same distance in the opposite direction, so roughly 2 and a little bit more to here. That point will be, see if I can fit all these labels, -1 minus root 5, comma 3. I'll erase those by the time I actually sketch this picture, but I just want to see those labels there. Minor axis, endpoints, -1 minus root 5, comma 3, and -1 plus root 5, comma 3. And write it down. Okay, they're all our information over here. So it's actually going to be very easy to write down. Let me erase some of these details now that I have it written on the side. Clear up my picture a little. So now we know we need to go 3 units in the y direction from the center to get to the vertices. 3 up, 3 down. It gives me vertices that look like they're located at -1, 6 and -1, 0. Just from looking at my picture. And the foci are going to be easy here, right? I'll call the first focus, I'll say it is 2 units above and below. So the first one I'll say is this one down here, 2 units below. That's at -1, 1. The other will be 2 units above the center. So that is -1, 5. Right, we've got all our information here. Let's just go ahead and sketch the picture. Label F2, F1, center, and let's just sketch. Good enough. Looks all right to me. Maybe we labeled, oops, maybe we labeled this vertex up here. And this guy down here, and those, I'm not going to label those minor ones, but let's get the center labeled. -1, 3. Kind of cluttered, but we get everything in our picture. So the next problem is a little bit different. In the next problem, we want to, just from a given description of some features of this ellipse, we want to come up with that standard form equation. X minus h squared over a squared. I'm just assuming a is bigger, or that it has a horizontal major axis. Might not be. The a and b might be switched. But this is the form, the general type of equation we're looking for. That's the standard form. And so we know the center is 1, 3. We know we have a focus at -2, 3 and a vertex at 5, 3. So let's sketch some of this first of all, before we even mess with the equation. 1, 3, there's my center. All these other places are measured around that center. We have a focus at -2, 3. Well, that tells us right away the foci are symmetrically situated on opposite sides of the center. So that's my center. I'll call this one of my foci. So the other focus must be 3 units to the other side. Did I do 3 units? Yeah, it looks good enough. 1, 2, 3, 1, 2, 3. I'll call that my other focus. And keep in mind, we can find those coordinates of the other focus very easily. It's just the center with 3 added to in the x direction. So it's 4, 3. The vertex, we have a vertex, so that's along the major axis. That's at 5, 3. Call that V2. Meaning the other vertex has to be the same distance in the opposite direction from the center. So V1's over here. Meaning V1 has coordinates, what we just took the center and subtracted 4 from the x coordinate. Well, here we can look from this picture and see that a squared, since a must be 4 units from the center, a squared is 16. C squared is given by the distance from the foci to the center. Let me clear this as the center, which is 3 units, so c squared is 9. From there, we use the equation to solve for b squared. Looks like b squared equals 7. So we should be root 7 units away, a little less than 3 in either direction from the center to get to our minor axis endpoints. Right, so the minor axis endpoints should be whatever the center points were, whatever the center point was, 1, 3, but to that y coordinate we will add and subtract root 7, how far we go from the center to our minor axis endpoints. So we'll do minus root 7 for one of them, and plus root 7 for the other. Okay, we've got our picture here. That's actually not so bad. Good enough. We've got all the big features. But we want the equation of that ellipse in standard form. This is going to be easy. The center, remember, that's our HK. That's where our ellipse was shifted to. So we know we have, and it looks like, before we even get there, it looks like I did choose the correct form. I have a horizontal major axis, right, from V1 to V2. That tells me that my bigger value, my A value, should be under the X stuff, which it looks like it is. So I actually did, just by chance, choose the correct equation, but you could see from your picture whether this equation should have A and B reversed, right? If you had a vertical axis of symmetry, you'd have A and B reversed. So let's see here. If I plug in the H and K are 1 and 3, right? HK is 1, 3. Then I have x minus 1 quantity squared over a squared plus y minus 3 quantity squared over b squared equals 1. And we know a and b, right? A and b, a is given by 4, so a squared is 16. B squared is given by 7, so we have y minus 3 over b squared is 7. And there we have our standard equation. Right, it's not so bad. You just want to think about the picture so you can pick apart these coordinates, the a, b, and c values very easily to fill out your equation. And remember, the center makes things very easy right away. Knowing the center does. Okay, so let's stop this video here. We'll pick up with this last little discussion of eccentricity and end with an example or two using that.